Why do elements react more dramatically than others? If we drop a piece of gold metal into water, nothing happens. Dropping lithium metal into water initiates a slow reaction in which bubbles gradually form on the surface of the metal. By contrast, potassium metal reacts suddenly and violently with water. Why do lithium and potassium react so differently with water, even though they are from the same family of the periodic table? To understand such difference, we will examine how some key atomic properties change systematically as we traverse the periodic table here in Chapter 7. By the end of this chapter, you will be able to describe the organization of the periodic table and explain its significance. Also, you will use the periodic table to identify the common ions form various elements. Use the concept of effective nuclear charge to explain the basis for observed periodic trends. You'll be able to identify periodic trends in ionization energies, electrons' affinities, and atomic radii. You will explain how the radius of an atom change upon losing electrons to form cation or gaining electrons to form an ion. And you will be able to write the electron configuration of ions. The discovery of chemical elements has been ongoing since ancient time. Certain elements, such as gold, appear in nature in elemental form and were thus discovered thousands of years ago. In contrast, some elements, such as technetium, are radioactive and intrinsically unstable. We know about them only because of technology developed during the 20th century. The majority of elements readily form compounds and consequently are not found in nature in their elemental form. For centuries, therefore, scientists were unaware of their existence. During the earlier 19th century, advances in chemistry made it easier to isolate elements from their compounds. As a result, the number of known elements were more than double from 31 in the 1800s to 63 by 1865. As the number of known elements increased, scientists began classifying them. In 1869, Dmitry Mendeleev in Russia and Lothar Meyer in Germany published nearly identical classification schemes. Both noted that similar chemical and physical properties recur periodically when the elements are arranged in order of increasing atomic weight. Scientists at the same time had no knowledge, or at this time has no knowledge of the atomic number, atomic weight, however, generally increase with increasing atomic number, so both Mendeleev and Meyer fortuitously arranged the elements in nearly the proper sequences. Although Mendeleev and Meyer came to essentially the same conclusion about periodical of element properties, Mendeleev is given the credit for advancing his idea more vigorously and simultaneous new work. So, for example, here was one of the prediction of Mendeleev about one element that at his time didn't exist, but he expected that it will be somewhere. So he expected that the atomic weight of this atom was 72, the density 5.5, the specific heat 0.305, the melting point was high, the color like dark gray, the form of oxide of this element it should be a XO2, the density of this oxide 4.7, the formula chloride for this element should be XCl4, and the boiling point for that chloride will be maybe under 100. And when they discovered this was made by this prediction in 1871, and when they discovered an element called germanium in 1886, they found that the atomic weight was 72.59, while he predicted a 72 atomic weight, the density 5.35, the specific heat 0.309, the melting point 947 degrees, pretty high. The color was grayish white. The oxide formula for germanium is GeO2, so he expected to be XO2. And the density was basically the same that he was expected. The formula chloride for germanium is GeCl4, and he observed that he basically predicted that it was XCl4, and the boiling point for the chloride was 84 degrees and he expected to be under 100. So that's why most of the credit was done to Mendeleev because he was a little more aggressive in his prediction and to create all this or share all this knowledge. Mendeleev's table was based on atomic masses. It was the most fundamental property of elements known at that time. About 35 years later, the nuclear atom was discovered by Ernest Rutherford, and 2 years later, the scientist Henry Moseley developed the concept of atomic number experimentally. The number of protons was considered the basis for the periodic property of the elements, and that's how the atomic number comes from. So basically, all this combination of knowledge were the one that established this atomic number that is the number that we use today to basically organize that periodic table. Periodicity is the repetitive pattern of a property for elements based on atomic number, and that's how this periodic table was organized. The following properties are discussed in this chapter: the size of atoms and ions, the ionization energy, the electron affinity, and some group of chemical properties trends. First, we will discuss a fundamental property that leads to many of the trends. Effective nuclear charge. The effective nuclear charge is this property that helps all, basically is the basis of all these trends. Many properties depends on attraction between the valence electrons and the nucleus. Remember that the valence electrons are those electrons that are in the outermost shell of an atom. Okay, so those are the valence electrons, the ones that are in the outermost shell. Electrons are both attracted to the nucleus and repelled by the electrons. The forces an electron experience depends on both factors. So that force is known as a defective nuclear charge. It's basically the difference between the attraction that they feel from the nucleus and the repulsion that they feel with other electrons. The effective nuclear charge ZF is found this way. ZF is equal to Z minus S, where Z is the atomic number and S is the screening constant, usually close to the number of inner electrons. The effective nuclear charge is a periodic property. It increases across a period and it decreases down a group. So from left to right, the effective nuclear charge increase, and from the top to the bottom in the periodic table in a group, it decrease. So here we have a figure to try to explain a little bit more that effective nuclear charge. Here we have the nucleus, and here we have the electron, and as we can see here, the blue one represents the force that has been attracted by the nucleus, and the red one is basically the repulsion that this electron feels from these other electrons, the ones that are part of the core. So the combination of all these forces is basically that is the one that is the nuclear effective force. Okay, so basically it's the combination between the attraction and the repulsion. Here basically are the red one represent the repulsions in this for from the inner electrons. About the size of an atom. Here we have a representation of two atoms that are colliding. These are the nuclei, and the shortest distance separating the two nuclei during this collision is twice the radii of the atom. We call this radii the non-bonding atomic radius or the van der Waals radius. This one, the non-bonding atomic radius, is known as also the van der Waals radii. Basically, the atomic radii for any atom in a molecule is equal to half of the bond distance d. So this collision basically create this bond between these two atoms, and that distance, half of this bonding atomic radius, is the non bonding atomic radius of the atom. And that way we can basically define the size of an atom. So how will be the trend of the size of the atoms in the periodic table? The bonding atomic radius is half the internuclear distance when atoms are bonded, as we mentioned in the previous slide. The bonding atomic radius tends to decrease from left to right across a period. Okay, and this is because the effective nuclear charge, that effective nuclear charge is increasing because you are increasing the positive charge in the nucleus. Remember that you're going from left to right, you are increasing the atomic number, you are increasing the number of protons, so you're increasing that positive charge cloud inside the nucleus, and that will also increase that force to pull those valence electrons, and that's why the atom decreases when you're going from left to right. But when you're going from top to bottom, the size of the atom increase because now you're in another level. So as the level from 1 to 2, the level number 2 is larger. So that's why it's increasing the size of the atom from the top to the bottom and decrease from left to right due to the effect of the effective nuclear charge on those valence electrons. Now, what happens when we form ions? What is the size of those ions? To determine by this size is determined by the interatomic distance in ionic compound. It's basically the same way as we determine the size of the atom. Remember also that in the periodic table, the metals are the ones that are going to produce the cation. So to produce a cation, you need to remove one electron from that element, and the anions will be produced by the nonmetals, the one that are on the right side of the periodic table, and they need to gain electrons, so in that way they can create these anions. And the ionic size is going to depend on the nuclear charge, on the number of electron, and the orbitals in which the electron reside. Basically, the same characteristics that we saw to evaluate the size of the atoms. Cations are smaller than their parent atoms. The outermost electron is removed and repulsions between electrons are reduced. Okay, because now we have going to have one less electron, but we're going to have the same amount of positive charge. So the positive charge is going to be larger than that repulsion between the electron, and that's why you are increasing that effective nuclear charge, and that radii of the cations are reduced. In other ways, the anions are larger than their parent atoms because you're adding one electron, and that electron will induce more repulsion between them, so that will increase that electron cloud, and that's why the anions are larger than their parent atoms. Okay, so the anions are going to be larger than the parent atoms, and the cations are going to be smaller than their parent atom because of the nuclear effective charge that they are experience. Okay, so in the cations, we're going to see that the ions, that those cations are going to have a larger effective nuclear charge as compared to their parent atoms, and that's why they are smaller than the parent atoms. While the anions, you're adding one more electron, and you're increasing the repulsion between all those negative charges, and that will increase the ion radius. So to try to make a little bit more clear, let's talk about the size of the ions. Let's talk about the isoelectronic series. The isoelectronic series are ions that have the same number of electrons. Down here we can see oxygen as an ion with -2, fluorine -1, sodium +1, magnesium +2, aluminum +3. So oxygen has an atomic number of 8. So in a way that we can have, for example, 10 electrons, we need to add 2 electrons. So that's why oxygen is -2. Fluorine is 9. So we add one more, and it's 10. Sodium has 11, so we need to remove one in a way that we can have 10 electrons in sodium, so that's why the ion is +1. Magnesium is 12, So we need to remove 2 electrons. So in that way is magnesium plus 2, and we have 10 electrons here. And aluminum is 13. So in a way that we can have 10 electrons, we need to remove 3 electrons from aluminum. So in this way, all of these ions, they have just 10 electrons. So they are basically known as an isoelectronic series. And the ionic size decrease with an increasing nuclear charge. Okay, we can see here that as the nuclear effective charge is decreasing, okay, basically it's increasing here because we're removing electrons in this way, to in a way that the nuclear charge is more positive, and that we pull more the shells to the nucleus. We can see as the nuclear charge is basically increasing to the right, the ionic radius is decreasing. Okay, so in this way we are also showing that in an isoelectronic series, atoms that has the same number of electrons, the one that has the higher nuclear charge or effective nuclear charge basically is the one that has the smallest ionic radius. We have another concept that is known as ionization energy. The ionization energy is the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. The first ionization energy is that energy required to remove the first electron. So we have, for example, one element, one atom is neutral, completely neutral. It has the same number of electrons and the same number of protons. So the energy required to remove that first um, electron is known as the first ionization energy. The second ionization energy is that energy required to remove the second electron. So now you have basically an ion and you're going to remove a second electron. So that's the second ionization energy. And these energies are different. The higher the ionization energy, the more difficult it is to remove an electron. So that means that not all the elements are going to be uh, easy to remove an electron. Okay, so some of them are going to be harder than others. So the higher the ionization energy, the more difficult it is to remove an electron. It requires more energy to remove each successive electron for the third or fourth uh, ionization energy if you need to remove other ions. Okay, so as we can see here in this table, in the 7.2, we have here the first ionization energy for the first electron is 496 kilojoules per mole. But to remove the second is 4,562 kilojoules per mole. It's a lot more to remove this electron, the second one. Here in magnesium is 738 kilojoules, and is for the second one is 1,451. But for the third, to try to remove the third electron is 7,733 kilojoules per mole. So basically, these are basically difficult to remove, okay, in this case. And so that's why most of the time sodium is just positive 1 and magnesium is positive 2. It's really hard to remove this third electron from the magnesium. The same thing with aluminum. To remove this one, the fourth electron is going to be pretty hard. You need to add a lot of energy to remove that electron. But the important thing here is that you can see that for the first one, because compared to the second one, is more easy, has a lot less energy required to remove that first electron. As for the second, as for the third, from the second, you need a lot of more energy to remove the third one, because now you have a more positive charge in that ion, and to remove another electron is harder in that way. So as you remove an electron, you are increasing that effective nuclear charge, and you're making those electrons closer to the nucleus. So that's why it's really hard to remove the second or even the third or fourth one in some of those ions. So let's see the periodic trend of the first ionization energy. The first ionization energy generally increases across a period, okay, and generally decreases down a group. The S and the P block elements shows a larger range of value of the first ionization energy, while the D block generally increases slowly across the period, and the F block element shows only small variation. So we can see that as you go from the left to right, okay, you are increasing that first ionization energy because, as we mentioned before, you have a higher effective nuclear charge, and that will make a little bit more difficult to remove that electron. So that's why it's increasing basically that ionization energy. That energy required to remove that electron is increasing from left to right in a period because you're increasing that effective nuclear charge. While when you're decreasing in the from you're going from the top to the bottom, the uh, first ionization energy decrease because now you are increasing that level. So those electrons are farther from the nucleus than the one that are before them. Okay, so then that's way it's more easy to remove electrons from the bottom part of the periodic table in a group from the bottom elements than from the ones that are in the top, because the ones on the bottom, those electrons, those valence electrons, are really farther from the nucleus as compared for the ones that are basically at the beginning of the groups. So basically here we have a representation. Smaller atoms have higher values. So we can see here that as you go from left to right, the ionization energy increase, okay, because of the effective nuclear charge is also increasing. While you're going from a group from the top of the bottom, basically is decreasing because here this one has a larger radius and they are bigger. So those electrons that are in the outermost shell, the valence electrons, are far away from the nucleus, and it's really easy to remove those electrons as compared to the ones in the top. Okay, so this one basically has a lower ionization energy than the ones in the top of those groups. The ionization energy depends on the effective nuclear charge, as I mentioned, and the average distance of the electron from the nucleus. Okay, so if you're comparing from a period, you need to look for the effective nuclear charge. If you're comparing in a group, you need to basically look for the distance of the electrons from the nucleus. Now let's talk about the electron configuration of ions. Cations, the electrons are lost from the highest energy level. If we want to produce a cation, we need to remove the electron from the highest energy level. So for example, lithium. Lithium, the electronic configuration for lithium as an element, as an atom, is 1s2, 2s1. Lithium as a cation is positive 1. So that means that we need to remove one electron. So that electron that we're going to remove is from the highest energy level, that is this one. So we need to remove this electron. So we're going to get rid of this, and our electronic configuration for the cation of lithium will be 1s2. Okay, because it loses one electron from the 2s that was for this example the highest energy level. Now, what about iron? This is the electronic configuration of iron. And one of the ions that could be produced by iron is iron plus 2, Fe plus 2. So that means that we need to remove 2 electrons. Remember that the electronic configuration, this order, is due to the energy, not due to the physical space. Okay, so if we want to remove, if we want to create a cation, remember that we need to remove those electrons from the highest energy level. That in this case is 4. It's not 3ds, d6. It's 4s2. This is the highest energy level, level number 4. So if we have some orbitals at that level, we need to remove electrons from that level. So to create the Fe plus 2, we need to remove 2 electrons from the 4s2. So our electronic configuration for Fe plus 2 is going to be this one without the 4s2, because we removed those 2 electrons from the highest energy level. For the anions, we need to create the electronic configuration of ns2 and p6. So fluorine, it was as an atom was 1s2, 2s2, 2p5. So because it gained an electron, now it's going to be 1s2, 2s2, 2p6. And that's the electronic configuration for the ion of fluorine. Now there's another characteristic that we can find in the periodic table, that is the electronic affinity. The electron affinity is the energy change accompanying the addition of an electron to a gaseous atom. So the electronic affinity is that energy associated when one atom gains an electron. For example, there's you see the atom of chloride, it add one ion and one electron, and you produce the ion of chlorine. It is typically exothermic. So for most element, it is negative. So basically, this is a reaction that release energy. So that's why that energy is going to be basically negative. We can find also in the periodic table a general trend for the electron affinity. Not much change in a group. Basically, in a group, there's no basically significant difference between those elements. Across a period, it generally increases. But there are three notable exceptions that include the following. Number one, the group 2A, because as the level is full, the group 5A, because the p sub level is half full, and the group 8, because p sub level is full. Okay, so those are basically the three more notable exceptions in the periodic table. But as a trend, basically increase from left to right. Now let's talk about some characteristics of metals, nonmetals, and metalloids. As we know, we mentioned before, the metals are basically the left side of the periodic table, the nonmetal at the right side, and the metalloids are basically the ones that are in this line, like star-shaped line. There are some difference between the metals and nonmetals. One of them is that the metals can create cations and the nonmetals tend to form anions. And one of the reasons for this is that, for example, sodium needs to release one electron, so in that way it can gain the electron configuration of the noble gas. So that's why for the 1A it's pretty easy to release that electron and produce a cation, because as they lose one electron they gain the electronic configuration of a noble gas. As the same way with the 2A, the magnesium, calcium, and all the other ones, for them, if they lose two electrons, they will gain that noble gas configuration. And that's what basically all of the elements are looking for. So that's why they can create this kinds of ions. In other ways, the nonmetals, for example, the ones that are in family 7, if they gain just one electron, they will have the configuration of a noble gas. The one that is in group 6, if they lose, I mean, if they gain two electrons, they will gain also the electron configuration of a noble gas, and as well the one family from the group 5. So that's why for the nonmetals is more easy to gain electrons and produce anions, and for the metals is more easy to release those electrons, to lose those electrons. So in a way they can form a cation, and at the same way they will have the electron configuration of a noble gas. So that's why they some of them, the metals produce cations and the nonmetal can produce an ion. So let's talk about some characteristic for the metals. Most of the elements in nature are metals. Properties of metals: they are shiny lusters, they conduct heat and electricity, and they also are malleable and ductile. Solids at room temperature, most of them with the exception of mercury. And also they have low ionization energy, form cation easily. So they are really has very low ionization energy. They don't want to gain electron. They want to release those electrons, so in a way that they can gain that noble gas electron configuration. The chemistry of metals. Compounds formed between metals and nonmetals tend to be ionic. So whenever you see a metal in a compound, you can think that that compound is an ionic compound. The metal oxides tends to be basic. So here we have nitric acid and water, and here we have nitric oxide. Um, Basically, we're gonna see in a few more chapters that there is a chemical reaction that is known as acid-base reaction. So an acid always react with a base. Here we add an amount of nitric oxide to the water, and also the nickel. Basically, sorry, this is nickel, the nickel oxide to water, and nickel oxide to the nitric acid. And as we can see here, when it was added in water, was insoluble in water, the nickel oxide, but it reacts with the nitric acid. So that means that because it reacts with the nitric acid, that metal is considered a base. So that basically most of the metal oxides, they tend to be basic. The nonmetals are found on the right hand side of the periodic table. The property of nonmetals include the following. They are solid, they could be liquid, or also they could be gas. It's going to depend on the element. The solids are dull, brittle, and poor conductors, and their large negative electronegativity forms an iodide. So basically, they are really easy to produce anions, as we mentioned before, because they can by gaining those electrons, they can produce the electronic configuration of a noble gas. The chemistry of the nonmetal, basically substances containing only nonmetals are molecular compounds. So if you have a combination with just non-metals, those molecules could be classified as molecular compound. And most nonmetals oxides are acidic. Okay, as different from the metals, the nonmetal oxides are acidic. So basically, this is a table with the characteristic of metals and non-metal. You can read this in the book also, and to have a little bit more clear those characteristics and how they can compare between the metals and the non-metal. And the third group that we have are the metalloids. The metalloids have some characteristic of metals and some of non-metals. Several metalloids are electrical semiconductors. So as the metals, they could be like they are like conductors and they can be used as computer chips. Elements in a group have similar properties. Trends also exist within groups. Group compare, for example, you can compare the group 1A, the alkali metals, the group 2A, the alkaline earth metals, the group 6A, the oxygen group, and the group 7, the halogens, and 8A, the noble gases. All the elements from each from these groups, they basically have similar properties. All the ones from group A, they have similar chemical and physical properties. From group 2A, from 6A, 7A, and 8A, the group trends are very similar in those groups. The alkali metals are soft, they are metallic solid, they are found only in compounds in nature and not in their elemental form. So basically, they are exist as compounds, they are not exist at elemental form. Typical metallic properties, luster, conductivity, are seen in them because they are basically metals. The alkali metals property, they have low densities and melting points. They also have low ionization energies. As we can see here, these are the properties of the alkali metals. The electronic configuration, you can see that this is the short one, that we have the electronic configuration of the noble gas. And as you can see here, if you remove this electron, you will have the electronic configuration of neon. If you remove this electron, you will have the electronic configuration of argon. That's why for the group 1, it's so easy to remove that electron to produce a cation +1. Because when you release those electrons, you're having that electron configuration of the noble gas. And also the different kinds of properties as the melting point, the ionization energy also is pretty low, atomic radius, density, and the melting point. Now the chemistry of the alkali metal is really exciting. As you can see here, this is lithium in water, sodium in water, and potassium in water. When you add any of those metals to water, they are really, really exothermic. They'll produce a lot of heat. And potassium, for example, they could produce also like flame. So they are really, really reactive, the alkali metals, specifically with water. Some difference in the chemistry reaction of the alkali metal, specifically with oxygen. Lithium reacts with oxygen to produce the oxide, the lithium oxide. While sodium, when it react with oxygen, it produces a peroxide, the sodium peroxide. And the other metals of that same group, when they react with oxygen, they will produce the superoxide, the MO2. So even though they are in the same group, they will react a little bit different in the presence of oxygen. And also they have a flame test. This is a qualitative test for alkali metals because those metals will produce a characteristic colors in flames. Here we have the lithium that's going to be red, sodium yellow, and potassium will be purple. Those are qualitative tests. So if we want to determine which kind of alkali metals we have, we basically do a flame test, and in that way the color will help us to determine which of the elements is. Now the alkaline earth metals, as compared to the alkaline metals, here we have the configuration of the alkaline metals. That is and this is the electronic configuration of the noble gases, halogens, and the 2s2, because we are in family 2, we are in the group, and then also in the block S2. All of them are basically in different levels, but with the orbit S2. Now, this family can produce cations plus 2. And this is the reason why, because you can remove those 2 electrons and you will have that electron configuration, halogens. And also here we have the different kinds of the properties of them: melting point, densities, atomic radius, and the um, ionic first energy ionization. Alkaline earth metals have higher densities and melting points than the alkali metals, and their ionization energy are low, but not as low as those of the alkali metals. The alkaline earth metals, as beryllium, does not react with water, and magnesium reacts only with steam, but the other alkaline earth metals react readily with water. So basically, beryllium and magnesium are a little bit more stable than the other ones. But most of them basically react with water, but as not as intense as the group one. Your activity tends to increase as you go down to the group. Group 6A, increasing the metallic characteristic down the group. So here we have the group 6A, all the characteristic, melting point density, atomic radius, and the ionization energy. Oxygen, sulfur, and selenium are nonmetals. Tellurium is a metalloid, and polonium is radioactive also as a metal. Now, in the first, basically 3 of them, if we gain basically 2 more electrons, we can have vision of the next noble gas. So that's why from group 6A it's more easy to receive those 2 electrons. So in a way that you will have now a full shell here, completely full shell, and this configuration will be the same as the next electronic configuration of the next noble gas. So in group 7A, we have the halogens, and the halogens have also the characteristic properties for this group. They are typically nonmetals and they have highly negative electron affinity, so they exist as anions in nature. They react directly with metals to form metals halides. And as the same way, if they just add 1 more electron, they will have the electronic configuration of the next noble gas. So that's why they're looking for. So in that way, they will have the electronic configuration of the next noble gas. So that's why all of this group are as an ion, they will be anion -1. And the group 8A, the noble gases, they have all here basically all the properties of the noble gases. They have very large ionization energy. They don't want to gain or lose any electrons. The electron affinities are positive, okay, so they can't form stable anions because they are really happy with the number of electrons that they have. And therefore, they are relatively unreactive. So they are non-reactive. The noble gases are non-reactive. And most of the time, they are found as monoatomic gases in nature. And with this, we finish our chapter number 7 the periodic properties of the elements.